So, Shubh, whenever you're ready. Shubh Agrawal is going to tell us about an equational calculus of interventions. Great, thanks.
Hi, everyone. So I'm Shubh from Northeastern, and I'm going to talk about our work towards an equational calculus of interventions. So first question, when you see the and we want to ask a question, which is to what extent does smokes, the variable in this program, cause cancer? And so the way we answer this is, like I said, we set the value of smokes, and the way we're going to do that is replace the mechanism that computes smokes with a free variable s hat, which represents this like act of setting the variable. And then we're only concerned with the impact on cancer, so we can throw away all those other returns. And then this is just an inference problem, and we can go ahead and solve it. We can sort of run inference twice, substituting true in for s hat or false in for s hat, and we'll get literally a number, and we'll get that maybe the probability of getting cancer if you smoke increases by 0.35. These are made-up numbers. I can't vouch for them. OK, so to relate this to some prior work in this area, here we have this full program. And studying interventions and causal queries in this setting is well studied by prior work like Omega and Cairo. And I think we're going to hear more about this later as well. But we want to generalize this somewhat. So the first change is that instead of having a specific mechanism, instead of knowing exactly what the program is, we might have unknown mechanisms. So we have some uninterpreted function that we know there's some relationship between the variables, but we don't necessarily know exactly what it is. The second generalization is the addition of what we call latent variables, or sorry, what are called latent variables. And this is where some variables, for example, genotype in this situation, we are assuming it's part of the causal mechanism, but we're not able to measure it. We don't even know what it exists or what genotype it is, and so we can't return it. And now we might ask the same question: to what extent does smokes cause cancer? And we do the same trick as earlier. We replace the mechanism that computes smokes, and we change the return value. But the problem is now this is no longer a program that we can run inference on. There's all these uninterpreted mechanisms. So the best we can do is estimate this by going to the real world. And what we would do is an experiment in the traditional sense. We would give half of the people cigarettes and tell them to smoke them, not give them to half of the people, and that would correspond to this S hat. And then we would measure the impact on cancer. Now, like we said, that's unethical. Instead, what we might do is an observational study, which just looks at whether people are smoking or not. And also, we might look at this other variable, tar, which can sort of help us understand the link better. And that would correspond to an estimate of this original program that we had. OK, but the problem is this is a completely different program and a completely different question. So why does having an estimate of that program help us? And this is where Unipearl's do calculus comes in. So what the do calculus says is when you have a distribution with a do in it, so do corresponds to this intervention that we were talking about, you can turn this into a do-free expression, so something that doesn't require any interventions and looks like normal pen and paper probability. with some series of equations. And these equations are what's called the Due calculus, which was first introduced in 1995 by Uta Pearl. So our position is that these insights in Due calculus and these equations can be applied to probabilistic programs as a typed equational theory. So what we mean by this is that this expression, the probability of C given due S, corresponds to these programs representing experiments like we had on the last slide. These the equations correspond to a typed equational theory, and we'll show an example of an equational rule. And this due-free expression corresponds to a program which uses the observational study as a subprogram. And the idea is that once we have an estimate of the observational program, and we have an estimate of that subprogram, then we can run inference to get an estimate of the program as a whole. And hopefully that'll become clearer later as well. But before we talk about what that final program looks like, I want to talk about what some of these equational rules look like. And I'm going to talk about maybe the most important equational rule, which is called observation intervention exchange. And this tells us when we can turn our interventional distribution, the probability of y given that we intervene on x, into a regular conditional distribution, like the probability of y given that we just observe x as normal. And the thing to point out, we've encoded this rule as what looks like the shape of a regular typed equational rule. And the things I want to point out here, so first of all, there's a major difference here, which is that our Due calculus rule has the introduction of this other variable y, which is the effect, like the variable whose effect we're interested in. Meanwhile, our rule doesn't have that variable at all. Instead, we're just looking at the return value of x. And so in that sense, our rule is a little bit more local than the corresponding Due calculus rule. There's another sense in which our rule is more local, which is that the Due calculus rule has this global independence criterion as a premise. So this is that y is independent from x in the full global model. So that's what the Due calculus rule looks like. Let's talk a little bit more about what our rule is. Our rule is talking about basically there are two ways to represent an intervention. So we start with this program E, which is a distribution, let's say a distribution over Booleans that has probability 0.3 of returning blue and probability 0.7 of returning green. One way of representing an intervention is throw away this original program that's computing it and return the value that we want to set the variable to. So in this case, green. And we'll get a Dirac delta distribution over green. The alternative way to do this is start with our same program and instead observe what its value is using conditioning. And this is going to give us a subdistribution. And then we have to normalize that distribution. And we, once again, are going to get a Dirac delta distribution. So hopefully it's intuitive that these two programs as sort of sub-expressions are equivalent. But like we said earlier, this is sort of a sub-expression. It's sort of local. And we're going to have to compose it with a bunch of other rules to turn it into, to get the full effect that we wanted earlier. So if we want to look at this final program that is able to finally simulate the intervention, it looks like this. So there's a lot of complex transformations that need to happen. I'll point out two things about this, and I'm happy to talk about this more later. But one thing is that our intervened variable s hat is used as a observation rather than as an input to anything. And it's not like it was in the original experiment. And the second thing is that we use this subprogram O, which represents our observational study. And we can see that this is the only unknown in the program. Everything else is just like a normal probabilistic program. And so we can do the same thing earlier of substituting in true and false for s hat and figure out what the answer is. And hopefully we would get the same answer, assuming we had some estimate for the distribution of O. So yeah, that's the crux of it. We want to turn programs representing experiments into programs which use observational studies that can simulate them. In future work, we want to work on automation for these equations. We want to work on some higher level reasoning that looks closer to what the Due calculus does. And we also want to work on a semantic model that can help us to validate the equations. In the extended abstract, we have a full equivalence proof and equational rules. So I'm happy to talk about that. And also during the poster session. And yeah, I'm also happy to take questions.
great talk. We have time for a question or two.
Thanks for this work. This is something I've been thinking about, and that's super interesting. And I agree. This syntactic PL approach is very nice compared to how the do calculus is set up. My question is: do you have any indication of completeness? So you showed one equation, and it's never quite clear for me what the do calculus takes. And I bet it's not a lot. Like it should be a finite amount of equations. But do you have them?
Yeah, so in this work, we don't make any claims about completeness. We have this fully worked example that's sort of like, for the do calculus, supposed to illustrate all the features. So like, we think probably you could generate a complete set of rules, but we're not going to claim that the set of rules that we have right now is complete.
Great. And maybe as we take our next question, could the next speaker come up and prepare?
Thank you for the nice presentation. You presented this equivalence between intervention and conditioning. And I was wondering if you could give an intuition for the correspondence between. Are you familiar with the backdoor rule in the do calculus, and what would that correspond to in traditional probabilistic programming?
Yeah, so the backdoor rule is sort of this. It's sort of an illustration of when you have a confounding common cause. And I think what's weird about our rules is that it doesn't show up directly. The do calculus rule for the observation intervention exchange does directly have the backdoor criterion. For us, it sort of like falls out of the other rules that we have that look like normal probabilistic programming rules. And it sort of like falls out in the composition of these rules somehow. So it's sort of hard to like explain exactly where it is. So maybe better to talk about that offline.
Okay, thank you.